Dear student, welcome to my channel. Topic of this video is support vector machine. In this video I am going to explain the quadratic programming for support vector machine. Now let us start. SVM is mapped as a constraint optimization problem. Objective of SVM aims to find a hyperplane, that is nothing but decision boundary, that maximally separates two classes of data points in high dimensional space. Margin is the distance between the hyperplane and closest data points from the class, that is nothing but support vectors. The goal is to maximize this margin, hard margin SVM, in the ideal case where data is linearly separable. Now this derivation is for hard margin SVM in which data is linearly separable. Maximizing the margin, this is equivalent to minimize the norm of weight vector W subject to constraint. The optimization problem is expressed as minimize 1 by 2 squared norm of the vector, and constraint is that ensure correct classification, that is every sample should be classified correctly. In SVM, this W into W, that is square term, is there. So it is a polynomial of order 2. That's why it is a quadratic optimization problem. And the optimization problem is to minimize this. So when we minimize this, we maximizes the margin between the two classes, and constraint is that all samples should be classified correctly. Quadratic programming. A quadratic function is a polynomial function with one or more variable in which highest exponent of the variable is 2. Constraint in optimization problem. The SVM tries to minimize a quadratic objective function, that is nothing but square norm of the weight vector, and it is constrained by linear inequalities, that is correct classification with sufficient margin. Lagrangian dual formation. To solve this constraint optimization, we use Lagrange's multiplier. The dual problem introduces variable alpha associated with the constraint. This transforms the problem into a maximizing a quadratic function of alpha subject to So we have to minimize 1 by 2 squared norm of the weight vector, and constraint is that all points should be classified correctly. Now this function can be represented as loss function. The parameters are WB and alpha. 1 by 2 squared norm of the weight vector minus, this condition is taken as for all points summation 1 to m alpha I, we introduce the Lagrange's multiplier which constraint to be non-negative, and the condition is that alpha I greater than or equal to 0, and this is the condition that for the subject to this, that is every point should be classified correctly. So now here we require to take derivative with respect to W and derivative with respect to B. Now Lagrange's is given by this equation where W is the weight vector, B is the bias, alpha is the Lagrange's multiplier for each constraint, yi is a label for each training example, xi is the feature vector for each training sample, and m is nothing but the total number of sample. Now here we are taking first partial derivative with respect to b. So when we take the partial derivative with respect to b, then at that time only this term, that is alpha I, yi and b is there. So as b is derivative is 1, so alpha I, yi, and we always make derivative equate to 0 because it is a minimization function, so equate to 0. So we are getting this. So this is a constraint ensuring that weighted sum of Lagrange's multiplier adjusted by their labels. So at last, when for m records, when we take the summation of alpha and yi, it should be equal to 0. This is one of the conditions that must be satisfied for optimality in SVM formulation. After that, we will take the derivative with respect to W. So when we take the derivative with respect to W, it will comes as a W minus, now here alpha yi and xi. Wt is nothing but only this is vector and this is again vector. So for multiplication we are just keeping this transpose sign. Then after that we are getting this equation, and we always equate derivative to again 0 because it is a minimization problem. So we are getting W is equal to alpha yi xi. Now here, okay, now here when we take the derivative with respect to b, partial derivative with respect to b and equal to 0, we get this condition, and when we take partial derivative with respect to w and equate to 0, we get this condition. Now we are putting this value of summation of alpha I yi and whatever the value of w in the original equation. So when we put the equation, so this equation is original equation, this is just expanded, that is 1 by w into w minus alpha I yi b alpha I yi w to xi and alpha I. So here we can see that summation of 1 to n alpha I yi is 0. So therefore this particular portion and this particular portion becomes 0. So it is nothing but summation 1 to n alpha I minus 1 by 2 w into w. Now we will put w here, so we will get summation. So as two summations we are getting, we are using I equal to 1, and for next j equal to I and j subscripts are used. So equation becomes alpha I alpha j, this is j, this is j, then yi yj and xi xj. So here this is scalar, this is scalar, this is scalar, but this is the vector quantity. Now we are getting this final equation after the partial derivative. So this is the optimized equation. Now we require to find out summation 1 to m alpha I minus 1 by 2 double summation alpha I alpha j yi yj and the product of xi and xj. Here alpha I, this is not a, alpha I and alpha j are the Lagrange's multiplier for data points I and j. Y and yj are the labels. It may be plus or it may be minus or it may be combination of both for data points I and j. X and xj are the feature vectors of the data points I and j, and this is nothing but the dot products of the vectors. Now when new point comes, then for a given test point x, the classification decision is made based on the following. So this equation we are generally using. So in my previous video we already see how the distance is calculated from the decision boundary. So summation 1 to m alpha I xi x plus b. So this is our equation. Only here the equation change because we are calculating now alpha I. So alpha I xi transpose into x plus x b. So this is nothing but unseen sample and this is nothing but our database. So in this way when new sample comes, we are classifying based on this formula. Now here if you see this equation, the main aim is to find out the alpha I, but to find out the alpha I manually is very tedious task. So for this calculation or to find out this Lagrange's alpha, various techniques are there. So for example, sequential minimal optimization, that is SMO, and quadratic programming are two methods to solve the optimization problem in support vector machine. So solving optimization problem is nothing but the finding the value of alpha I, and alpha I should be greater than or equal to 0, and for all data points that summation 1 to m alpha I yi must be 0. These methods are employed to find out Lagrange's multiplier alpha I, also called the dual variables, that maximize the margin between the classes while considering the misclassification penalties. Specialized solvers like libSVM or CVX opt implement the quadratic programming algorithms to calculate the values of, in some literature it is using alpha and some literature is using it lambda. So basically to calculate that particular Lagrange's multiplier constant, so for all points. So this is all about the quadratic programming for the hard margin of SVM. So to manually calculate the alpha I is not easy, but in my next video I am taking a very simple problem in which we already declared the support vectors, and based on that we are calculating the W and the B values.